Right. So welcome back, everyone. So this session particularly, yeah, this is a hands-on session. So the title is anyway hands-on on reionization simulation. As many of you are anyway using various reionization codes, etc. So I'm not going to focus on any particular code, but for this session, let us just discuss the philosophy or principles. If somebody among you want to write your own code, what are the requirements and how you do it. So basically, yeah, I mean, there is many of us will be involved in this particular tutorial. Now, of course, like this picture we have seen in my previous lecture, and we are again focusing on this cosmic on epoch of reionization part. For this demonstration particularly, I will be focusing on epoch of reionization, only ionization thing. Okay. So Ilian has already talked a little bit about what are the requirements, etc. If you are trying to simulate epoch of reionization signal, n-body simulation, credit transfer, etc. So let's take a little bit a deep look. What are the requirements for a simulation? We are trying to simulate this brightness temperature in a cubicle, let's say in a cube. So, and this is a signal from hydrogen. So first of all, we need to know how hydrogen is distributed. That how can we get that information? So we have information about, let's say, the power spectrum from TMB or whatever, like you choose your cosmology. And the redshift of your interest, choose one redshift, or let's say our fiducial redshift is 9. We know what the power spectrum should be at redshift 9 using your cosmological model. You can also took an alternative way that you start running n-body simulation. That also, like, you have to initialize with a initial power spectrum. For that also you need to know what cosmology particularly you are choosing. So the demonstration which I will be showing here, that will be on lambda CDM. You can choose your own type of dark matter model as well, a Z, worm, whatever. That will change your density field. Now, one easy thing for n-body simulation is that if you do that only dark matter only simulations, if you add hydrodynamic the gas into the simulation, you will get a better distribution of hydrogen, but again, like that will be costly in terms of computational resources. So many people just do n-body simulation only using dark matters, and assume that whatever density field they will get from the n-body simulations, our hydrogen density actually follow that one, and which is true at large scales. If you go at a very small scale, like parsec scale, that will not be the case, but the scales which we are probing, we are interested, this is fine. If you start with a dark matter only n-body simulations, and eventually get a distributions of your dark matters, which will give you the density fields in some grid, for example. Here for our demonstration, we are using a grid of 300 cube. I have provided you one such density field, which is basically density over density 1 plus delta. This is the input folder of one normal. I mean, you have the folder. So there are other approaches as well, which is semi-numerical. We just exploit the fact that we know the power spectrum at redshift 9 or whatever redshift you are interested in, and just from a Gaussian random distribution, they basically produce a density field in grid that satisfies that power spectrum, which is fine. Like, okay, ultimately what we need is 1 plus delta, which is over density, right? So this is one important quantity, and now from this input folder density field which I have given, you will be able to produce a density map, something like this. You have the Jupyter Notebook script. Maybe if you start running that one, that will produce a figure something like this. Now you see, this is 1 plus delta, and there are regions which are quite high dense. So these are the probable locations where dark matter halos form. There is a dark matter distribution, but dark matter halos will be isolated, let's say, localized objects, which will eventually host stars or galaxies, something like that. So you need to know, in addition to this density field, we also need to know the locations of dark matter halos, because those are locations of sources. So, I mean, this is a task which you can do. So, given this distribution of dark matter from, let's say, in-body simulations, or even if you start from your semi-numerical approach, we need some prescription which kind of locate the dark matter halos. That can be done in in-body simulation. There are approaches like spherical over density, friends of friends algorithm, Rockstar, Amiga. So you use these type of codes to find clustering of dark matter particles, which we will eventually say that, okay, these are like the dark matter halos. And from in-body simulation, it shows that, okay, there is a distribution of dark matter halos, and that distribution particularly depends on what type of dark matter candidate you are considering. For example, if you are considering lambda CDM cosmology, and you will find that, okay, there are lots of small dark matter halos compared to large mass dark matter halos. While if you use, let's say, warm dark matter or fuzzy dark matter, you will find that, okay, initially when you are going from large mass to small mass size, it was increasing, and then eventually it will drop. This kind of distribution of dark matter halos depends on what type of cosmological models you are using. Now we started from a distribution of dark matter. We now know, say, in this box, this room, we want to simulate brightness temperature, 21 centimeter brightness temperature. We started with a distribution of hydrogen gas. We now localize that at which position these sources are, which are dark matter halos, which will eventually host a galaxy. So in semi-numerical approaches also, there are methods, approximate methods, but people can use, for example, using a polar fraction, or there are analytical prescriptions of finding dark matter halos from 1 plus delta. So people use these, for example, this popular code 21 cm fast that uses polar fraction approach. Initially, it used to, I mean, it was using this analytical or semi-analytical prescriptions of halos, but there are challenges. Like if you want to get a halo list from 1 plus delta, the density contrast field, there are several challenges, so they are avoiding, and they are just using a polar fraction which is dependent on 1 plus delta. Now good, so we now know that these are the positions where source will form. Now we need to know what type of source formed. So this figure is showing that given this density field, these are the locations where dark matter halos are. Not everywhere, but quite a significant amount of dark matter halos are in that particular slice. And the color bar is showing the mass of each dark matter halos, right? Now we need to know what type of source actually are inside the dark matter halo. That could be a galaxy, that could be a galaxy which also hosts high mass X-ray binaries, that could be a quasar, depending on your source. Type of source, the SCD, spectral energy distribution, that will differ. Now, why I'm saying this, let's say in your model, if there are some quasars, that will emit lots of ionizing photon. So that will eventually will create a big ionized region. It will ionize many hydrogen around it, compared to a just galaxy. So it is important to now know what type of sources we are using or present at our mock universe. So we need a source model. We previously had a dark matter halo, and at that particular location or inside that dark matter halo, what type of source had formed. For that prescription, we need something that is known as source model. That will basically connect the dark matter halo to source emissivity, emissivity of UV photon, etc., and which will eventually, this radiation from the source will create ionized region like this. For that, of course, like now source are started emitting photons, UV photons, Lyman alpha, X-rays. Those will propagate from the center of the source, and it will basically try its own job in interacting medium. Some will ionize the interacting medium hydrogen, some will heat up, some will be used for Lyman alpha coupling, things like that. So for each photon, we need to know the prescription or with which we can determine the flux of that particular type of photon. So this is one can do using full radiative transfer simulations. Ilian had talked about this one. One can use approximate method. The approach which we will use in this particular tutorial is 1D radiative transfer. I mean, given a source, let's say a galaxy, we will now determine what will be the size of the ionized region around it. That will be determined using 1D radiative transfer. We will know that, okay, this many hydrogen, this many ionizing photon has been emitted with a ACD, and that will be propagated from the center of the source. So it will depend on what is the edge of the source, and it will provide that, okay, this big, maybe bigger ionized regions are around that source. Right. So for this demonstration, we are going to use this source model that given a dark matter halo of mass M halo, the stellar mass within this dark matter halo is proportional to this is star formation efficiency time omega b, this is the baryon content, and omega matter. So this gives us the stellar mass content within this dark matter halo of mass M halo. Later, we defined, actually, we will use 3 parameters for this scenario that given this amount of stellar mass M star, how many ionizing photon has been produced from that source? That will be this. So there is this parameter zeta. So per second per stellar mass, this amount of ionizing photon, UV photon, has been produced from the source. We also use a quantity M min, which will control how many sources are actually contributing to ionization. So given this is the map, here we take contribution from all the dark matter halos which has mass above 10 to the power 9. But if you choose a M min of, let's say, 10 to the power 10 or so, you'll find quite few dark matter halos are actually contributing. Right. And there is another factor which we are introducing. This is to basically, we will use same model for our next Bayesian framework. And this is for a model where we will assume that heating is happening, but there is no heating fluctuation. Heating is uniform. So this is like a constant factor over space. So these 3 parameters, let's say, we consider, and depending on that, so you can imagine that zeta will determine how big a ionized region will be around a source. M min will determine that, okay, how many such regions will be in my simulation box, right? This is one quantity that will be determining what will be the amplitude of power spectrum, brightness temperature power spectrum, or the brightness temperature amplitude. Now we need a prescription to determine how big the ionized region will be around a source, right? As I said, that can be done using 1D radiative transfer, which shows that, okay, given a stellar mass, if you do a detailed calculation of photon transfer from this source, then the ionization fronts that look something like these, and these are for different edge of that source. So after 1 mega year, it will propagate to do this distance. The ionization front will be, it will propagate further, or a time of 3, 5, 10 mega year. Now, the fact is that, let's say a galaxy just formed, okay? And there are very new stars. What it will happen that the stars will populate metals in it. Its intrinsic spectrum, it will modify. So eventually what will happen that after a certain age, UV content of that galaxy will be actually reduced. It's not like that galaxy will radiate like infinite amount of time. So here, using this thing in keeping in mind, so we will use a constant age for the sources. Now, thing is like what analytical prescription shows that there is a formula for estimating the size of the ionization front given your emissivity in gamma dot. So this quantity is controlled by our zeta. You choose a zeta that will give you this number of ionizing photon per second per stellar mass. So if you use that particular prescription, which fits very well this analytical prescription and the results from the 1D ray transfer, so we can just use the simple prescriptions that given an age of the source, it will give you the size of ionized regions. So this is linked to the Stromgen sphere, which shows that, okay, if a source is radiating, the ionization front, which will of course get bigger over time, that will go bigger, but eventually this will saturate. At some point, what will happen, the amount of radiation, UV photon, which has been emitted from that photon, from that source, will be, I mean, there will be a opposite process named as recombination, you know. So there will be a balance. So at equilibrium, it will reach to a particular radius that is called Stromgen sphere. And using this particular formula, so there is a dependence on Stromgen sphere, and there is a formula one can end up with, which one can use. So this is a particular approach I am taking, and this is very different than all approaches which different codes take. But only to understand, let's say, what will be like the requirements and what will be the philosophy if a new PhD student want to simulate signal or heart signal in a simulation box. Right. So another thing which we need to account is that now let's say there is two sources nearby and their individual ionized regions start to overlap. So given the size of this Ri around a source, I can just create a region and I just make that, okay, this is ionized. I just make XH1, which is neutral fraction to 0, and all over other part of my simulation box, ionization fraction will be 0 or neutral fraction will be 1. But if this ionization regions, which are spherical in nature, we are using 1D approach, start to overlap, then what will happen? So there is this region, for example, in black or here as well. You see that some way there are some unused ionizing photons. So one approach need to be calculating this amount of unused ionizing photons and distributing those in some way so that that will be used in ionization. One easiest approach is that, okay, you just start calculating what will be the contribution from this source, S2 and S3, and start to increasing the size of these ionized regions of each sources so that these photons are some way used. Approximate method, but at least all the ionizing photons are now used. So this is one overlap corrections needed, which many of like the previous versions of code didn't use, including 21 CM fast. They say that they are using in the latest version, but previous version were not using this one. But this is a very important factor. If you are not including the overlap correction, then okay, you're basically, there will be photon loss, which is not physical. Now, let us go through the script which has been provided to check whether this is working and you are able to produce at least some results which I have shown. Before I go to a little bit description of, let's say, the brightness, temperature, or ionization fractions. How many of you are able to work with the Fortran code which was provided? How many are not able to do that? Mac. Right, okay. So I'll ask you whether like the basic philosophy of, let's say, reionization, which I was trying to explain. If you have any questions from there, confusion or anything like that. I mean, demonstration is fine, like we will be able to do at some point. And this anyways doesn't make much sense because you have your, anyway, you will probably use some other codes. But the basic, let's say, philosophy of what are the requirements and how to do it, this type of concepts should be clear. If you have any question regarding that particular point, you can ask. Go ahead. (3D) is very costly. So 3D means like now you have to rely on ray shooting. You have a source and you shoot rays a different direction, which will give you, of course, more accurate result, no problem. But this is very costly. It needs huge amount of resources. So last particular lecture of today's this series of lecture is on pi-C2 ray. I'm not sure that will be done or not. This will demonstrate that use of 3D ray transfer is first of all is very time consuming, resource consuming. And second thing is the results which you will get from this 3D type of calculations. Using 1D ray transfer type of calculations also broadly agree with those. So there are like tested on several scenarios and we found that, okay, it exists quite well. Although this is very much approximate way, but still it works pretty good compared to a fully ray transfer type of simulation. You want to? Right. At this point, like if you have any questions, I know that, okay, many of you are using various other codes. If you have general questions regarding, let's say, simulations, that also you can discuss. So,
everyone just run that Docker run file, so you will be inside your Docker. No. Once the Docker is open, you can go to the Fortran file and then execute the commands. Yeah. Once you are inside the Fortran directory, do make clean and then again make the file, and then you can run the execute file. It's already available. Yeah. It will run all the simulation for all the parameters. And if you're interested, you can check what does the execute file does. Any problem, let us know. Yeah.
At least some of you are able to run that code. Okay, good. मैक में देखते हैं और क्या करें. So maybe like, okay, we stop like running the code ourselves. If there are any technical difficulties, let us figure out after this session. Okay, so a few more points I wanted to highlight here, which will be useful for our next lecture. Some of you are able to produce like maps like the neutral fraction, which has been shown here. And the script if you have run entirely, then that has produced many such scenarios. So we have varied different parameters, zeta m min and this 1 minus t cmb by ts, that to show like different scenario and the impact of different parameters. Now what we want to do is actually this differential brightness temperature estimate, right? That was our aim. So far what we have done is that we have started using a cosmology, we have used the density field, we have used the halo list, we have used a property of source, and we have estimated what will be the ionization fraction field or neutral fraction field in this box. Now using that, we need to generate a differential brightness temperature map, and one can use this equation. Today morning, you heard from Kanan that this is a optically thin limit, so one can come up with such a formula. Now, in our model, we are using a uniform TS. Right? So this particular term is basically a factor, it's a constant factor, not a, spatial dependence. This thing you have plotted, this has a variation over space. We will ignore the velocity term for now, and these are cosmological parameter values. So you put, this field which has a function of spatial coordinates, and you will be able to estimate the field of 21 centimeter signal brightness temperature. Easy. So these are the assumptions which we are making. We are ignoring the velocity effects and we are assuming uniform spin temperature, and we are using this equation, dropping the velocity term, right? And doing that, you will be able to produce brightness temperature cube, and this is showing a slice from that. Now, you can, so there is a fluctuation term, and previous lecture I was talking about the power spectrum estimate. So you basically estimate the power spectrum. Why I am taking the power spectrum particularly in this context is that for next lecture, we will be using a power spectrum for some type of inference on this model parameter. Now the thing is, we are using three parameters: zeta, ionization efficiency, right? A min, which will control the number density of sources, and 1 minus t cmb by ts, which is controlling, let's say, amplitude of the power spectrum or level of heating. Now here you see that starting from zeta equal to 1, changing it to 3, and again changing it to 5 is actually increasing your ionization fraction. So region in yellow, these are ionized regions. Regions in green, these are actually your absorption signal, neutral region, but that is emitting in absorption. No heating happened. So here we are assuming this 1 minus T gamma by Ts, this factor to be minus 12, which means at regime 9, every calculation, all these calculations are happening at regime 9. This means that reionization happens only due to galaxies, which doesn't have any X-rays, right? It created ionized regions, but hasn't heated beyond the ionized regions. Those remain cold. There is line of saturation. This is the scenario which we are considering. Now you see that depending on the ionization fractions, power spectrum is nature of power spectrum as a function of K, the wave number, that is changing quite significantly, means that, okay, there is a quite significant impact of the zeta parameter on power spectrum, which means that it is good. Given a measurement, now we can actually constrain zeta. Same is also true for M min, where we are varying the M min from 10 to the power 9. This is probably 5 into 10 to the power 9, and this is 10 to the power 10. While, of course, like for this case, there will be so many sources which are contributing to reionization. Zeta is fixed here. So ionization fraction is, of course, much larger compared to other two cases. And here as well, like you see that, okay, the power spectrum is very much sensitive to M min parameter. While this T gamma, this factor particularly, 1 minus T gamma by Ts, you see that shapes are same, only like, okay, the amplitude wise, it is scaled. Because this is basically a number. It's not creating any additional fluctuations, but only it is changing the amplitude of the power spectrum at all the scales. So starting from like minus 12, which is dominated by absorption signal, and some part is ionized, right? Strength of your absorption signal is very strong. It's like, okay, average wise, it will be probably minus 250 or so. You see that, okay, some part you will probably find minus 600 millikelvin of temperature, but average wise is, let's say, minus 200 millikelvin. When you decrease this factor to, or increase this factor to minus 5, of course, amplitude wise, because in power spectrum, this square will be multiplied. Right? This is a factor, a normalization factor basically will go into power spectrum amplitude. And for that, there is a drop in power spectrum from here to here. Although like the scale dependence is same, only amplitude wise, this is rescaled. And the same is happening. So this is the scenario, typical UR scenario, which all of you are familiar with, is that ionization and while other neutral part is heated. So spin temperature is much, much larger than the CMB temperature, which will give 1 minus T gamma by Ts factor to 1. This is a known scenario, which again like drop this power spectrum and with a, let's say, a constant factor applicable to all the scales. So with that, now we have a broad understanding like what parameter is doing what. Okay? If you increase zeta parameter, your ionization will increase. If you increase M min parameter, you will basically ionization will drop. And if you increase, I mean, the amplitude of this parameter, if you increase, then your power spectrum will increase. But overall, like this particular factor can go from minus 12 to 1. And this is a standard cosmological scenario where we know the background IgM temperature if there is no heating. Now with this, I would just like to highlight what are the available codes which you can use, and I know that many of you actually use some of these codes. All the statistical codes, for example, which I was describing, and many of those actually calculations are available in this particular code named tools21 semi. So there is script code written by Tirth's group. You can discuss the detail of this code with Tirth is here. Anyway, this is a 2LPT based UR simulation code available. So you can visit this one and download. This is also fast, very comparable to codes like 21 CM fast, although this doesn't include the spin temperature fluctuation. They are working on it. Hopefully that will be added soon. Riyan Yoga. So this is a n-body simulation based code. We start from, let's say you choose a cosmology, it will distribute particles and it will, in a box, it will do an n-body simulation, it will find halos, and after that it will use a source model to produce ionization fields available in this website. Grizzly, some part of the Grizzly philosophy I am using for this tutorial. Although like entire Grizzly, this thing is based on n-body simulation, we are using n-body simulation outputs, density and halo list, which I have provided. This is a post-process based method based on 1D ray transfer. This code also simulate cosmic dawn signal, spin table fluctuation, which I haven't touched at all in this particular demonstration. There is 20 NCM fast. I think all of you know about it. It's a very popular code based on semi-numerical excursion set principle, and it can both simulate UR and cosmic dawn scenarios. There is a code, IC2 ray. This is a 3D ray transfer based code. Again, post-processing from n-body simulations. This is a GPU based code. Yeah, maybe like it needs some resources, but whatever like it will produce in terms of ionization maps, those will be much more accurate compared to what we are doing here. There is another code named Baron, which is again 1D ray transfer based code, but this is a more or less a Python version of this Grizzly. They follow a similar approach and can be found here. There are maybe other codes, I don't know whether those are publicly available or not. So yeah, feel free, like you define your problem and choose what code you want to use. Most of the codes has a reasonable amount of documentation, source model, etc. But what I would like to do is that take out point from this particular 1 hour lecture should be understanding the basic philosophy of a reionization simulation, not like understanding what are the source model one particular code is using. Hopefully that is clear. If not, please don't hesitate, just ask question and discuss those things with me. Right, so way forward is that, okay, just before way forward, recap that we talked about a 1D ray transfer based simplified Grizzly model, which takes a few source parameters. Given this source parameter into the code, it will produce brightness temperature cubes. And from that, we basically produce power spectrum. Why power spectrum? Because this is one quantity, as I'm repeating, that radio interferometers are targeting, and they are producing good results in terms of upper limits, but still very useful. And we are going to use such upper limit results, from Lofer 2020 paper to do some Bayesian analysis on source model. Sorry, this changed now. Okay, I think I don't have any slide anymore. So fine, so the next task will be that we will use such a upper limit, which is saying that, okay, using 10 hours of observation at raceme 9, the power spectrum will be somewhat below these numbers. The next tutorial will use this particular observation, that these are the maximum limits of power spectra at certain scales. And the task is that given this parameter set, what can be constant? What can be the inference constant on these particular parameters, given the source model which we are using? Uniform heating, ionization is basically driven by zeta. Min is driving the patchiness of the ionization. And we would like to see whether any type of models are ruled out, or what can be told using this particular upper limit result. That will be the second exercise. So, okay, I'll stop here and ask for question if you have any. in remaining, let's say, a few minutes. Otherwise, like, okay, if you were doing the plotting stuff or understanding the file format, etc., that you can continue. If you have any specific questions regarding the simulations or something, let's say, related to the what I talked before lunch, that we can discuss at this moment. Yes. Which are the access sources? Yes, so what the theory suggests is that high mass X-ray binaries is one of the very common X-ray sources. So the thing is, like, very early galaxies, there its mass function is very different than the local galaxies. So that prone to be very massive star content. So those massive stars, they tend to form black holes. Say, okay, if many black holes are forming, so they will eventually produce binaries, which will emit X-rays. These are like galaxies. Same philosophy can apply that, okay, the center of this galaxy can also collapse, form a black hole, eventually powered by accretion. So quasars, but we don't see that many quasars at very high redshift, but seed of quasars which we find, let's say, in our local universe or universe around redshift 3, 4, etc., seeds lies actually at very high redshift. So they are proved to be that mini quasars, which are like the mass of the black hole will be very small, but mini quasars can be one of the X-ray candidate at high redshift. Other physical processes, I mean, people use various different X-ray emission mechanisms, but in terms of like sources, these are two are, let's say, very commonly used sources: high mass X-ray binaries and mini quasars. Now, quasars, if somebody wants to use quasars, so there is a more or less whatever understanding we have that quasar population, they drops very drastically if you go beyond redshift 3 or so. But this recent observation, for example, from JWST, which is suggesting that quasar population is actually not that less, which we used to think before JWST. Now, if that population goes up, then there will be a significant amount of heating from quasars, not mini quasars. Those are regular type of quasars. Yeah, it depends on what type of source we use, but frankly, like the what particular fraction of X-rays are coming from which type of source, this is not known. People do a rough type of modeling that, okay, we use uniform type of modeling for all the dark matter halos. It may not be the correct picture. For sake of, let's say, simplicity, people just use a simplified model for ionization as well as for heating. Yes, I mean, so the lifetime of these massive stars are actually short-lived. So that, yes, yes. That is why, like at high redshift, like the formation of high mass to hit this thing. These are all like model dependent. As I say, like this may not be like the X-ray properties of galaxies. This may vary galaxy to galaxy. But for simplicity, like, okay, we actually just use a uniform type of behavior for all the galaxies. It may not be true. So yeah, I mean, it's all depends on what type of modeling you are using. So that's why the inference, for example, or the predicted signal, which I'm showing here, always you have to keep in mind that various assumptions has been basically taken to derive to that point. Yeah, I mean, that's fine. Like it is giving us a quantitative representation of the signal, but it's not like you just take it granted that this is the This is the correct picture in known light. There is a huge uncertainty. It could be anything. This is a rough estimate or representation of the signal, let's say. Anything else? If not, probably we break for a coffee.